Oh, hello everyone. Welcome to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Maxime Fairon from the University of Paris. He will speak on around van den Bergh double brackets. Yes, around van den Bergh's double brackets. Yeah.
Exactly.
Mhm.
Okay, perfect. So thank you very much for the introduction, and let me thank all the organizers for the opportunity to speak today. Because as you will see, the topic, it's really some notion related to Poisson brackets and generalization of Lie brackets. So it's something that really sits in the general subject of non-associative algebra, I would say. And I really hope that I will convince you about that. So my plan will be more or less to speak for quite some time about this notion of double brackets that is due to van den Bergh. Okay, it's something from the year around 2004, and it was published in 2008. So something that has almost 20 years, let's say. But it's extremely convenient. At least that's how I discover it. It's really convenient to, let's say, do computation using a Poisson bracket on some space of matrices at the level of some non-commutative algebras. Okay, so this is the thing that I want to advertise today. And after just recalling what are the main feature of these double brackets of van den Bergh, I will explain some, let's say, tweaks that you can do with the definitions that I introduced later on with Colin McCulloch. Right, so what are these double brackets? Well, to understand them and have an idea why you should care about those, let me just remind you about a general principle that was introduced by Kontsevich and Rosenberg around the year 2000, and which dictates some philosophy to do new, let's say, to search for new object on associative algebras based on some things that may be very standard on commutative algebras. Okay, so to understand this philosophy that I want to introduce, what we do, we just fix some associative algebra A at the moment over a field of characteristic 0. If you want, you can take it algebraically closed and maybe just work over C if you want. Okay, and what is important to understand this principle is not to look at A itself, but to consider all its representation spaces. Okay, so the nth representation space that we will denote rep NA, well, you can define it as a scheme using its functor of point like this. Otherwise, the best way to understand this is just the space whose points are really parameterizing representation of the algebra. Okay, so a point in that representation space is just a way to assign to each element of your algebra n times n matrix, satisfying the relations in your algebra. That's really the best way to understand it. And what is very convenient as well, if you want to think about that a bit algebraically as well, is that the coordinate ring of your representation space is just generated by some matrix symbols, these A, I, J. So the little a is just an element in your algebra, and the indices I and J just run between 1 and n. Okay, so just think of this A, I, J as being a function on this representation space, which at a point will just return the matrix representing the element A, and then look at the ij entry of it. So this is really what this matrix function is doing. Okay, so with that, we know what the nth representation space of our algebra is. And then what is this Kontsevich-Rosenberg principle? Well, it's something vague, really, just to give you idea of to find new structure, but this vague thing is as follows. Okay, to quote them, okay, what we want is a non-commutative structure of some kind on our algebra, which should give an analogous commutative structure on all representation schemes. Okay, so the general idea is that you have some structure, let's call it S, on some commutative algebras that you like. Okay, so for me today, the structure that I will like are just Poisson brackets. Okay, and what I will want to do is to understand Poisson brackets in some way at a non-commutative level. I want to define some non-commutative version of a Poisson bracket in the category of associative algebra. such that whenever I'm using this map at the top going from an algebra to the nth representation space, okay, using this representation functor, I want to get the usual structure, which would be a Poisson bracket. Okay, so this is the general philosophy that I want to follow today. And just to give you a quick idea of all things are doing, I will directly give you the definition of these double brackets of van den Bergh. Okay, so some notation first. Throughout the talk, we will be working a lot with the notation A tensor 2, or A tensor A. So it just means that you take an algebra A that you fix, and you take the tensor of this algebra over its base field K. Okay, so from now on, I just remove always the decoration for the base field in the tensor product, because all tensor products are over K. Okay, then on A tensor A, you have an obvious multiplication like this. And what's quite important, and that will be used repeatedly, you have a swap map. Okay, so this tau 1, 2 is just swapping the two factors in the tensor product. And now what I can do is just give you the definition of a double bracket. Okay, so just to give you the hint of what it is, if you have a Poisson bracket and you forget about Jacobi identity, you have just an operation which is antisymmetric and a derivation in each argument. Okay, so it's a biderivation, an antisymmetric biderivation. A double bracket is a non-commutative version of that, as we will see. Okay, so more precise. Oh, sorry, is there a question? No, just me. Okay, but anyway, if someone has a question at some point, don't hesitate to interrupt me. So the first thing to have a double bracket, okay, let me just say, and this is important, that it's an operation which will take two arguments in your algebra. Okay, so it's going from A tensor A, sorry, from A times A to A tensor A. Okay, so that may be the only difference with what you would usually do with a Lie bracket or a Poisson bracket. You are not going from the vector space to itself, but here we are going in this algebra A tensor A. Okay, and the rule that we are requiring are the following. So the first rule, it's almost an antisymmetry rule. Okay, it's telling you that if you swap the two arguments, then, okay, so if you swap these two guys, then what you want is to have a minus sign, in which case it would be antisymmetric. But as we will see, we need a bit more. We need that it's cyclically antisymmetric. So we need not only to have a minus sign appearing, but also to swap the two factors. That's the first rule. And then to have an analog of, as I was saying, of non-antisymmetric biderivation, we need our derivation rules. And so the first thing that we can do is just say, okay, in the second argument, we require the derivation to be the outer derivation. Okay, so meaning that the left factor here, B, will be multiplying on the left the first tensor factor. And here the second factor, the C, appearing in the second argument, will be multiplying on the right the second tensor factor. Okay, so this is this outer derivation because, as the name is saying, it's multiplying from the outside. And then in the first argument, you can require also a derivation rule, and here you require it to be an inner derivation, so it's multiplying from the inside. So the A will be multiplying the second argument from the left, and the D will be multiplying the first argument from the right. Okay. And here, let me just already say quickly, the second derivation rule, so this inner derivation, you cannot take it randomly. Basically, it's completely determined by the rules 1 and 2. Okay, because of the cyclic antisymmetry, the two derivation rules are equivalent. Okay, right. So why is this notion of a double bracket interesting? Well, for the following reason. What van den Bergh has proved is that if you have such a double bracket on your algebra A, and if now you go according to this Kontsevich-Rosenberg principle, you go to representation spaces, okay? Then what's happening is that there is a unique GLN invariant antisymmetric biderivation, which satisfies some rule that is written here. Okay, so let me just spell out this rule. So if you remember, I told you that the coordinate ring of this representation space, it's generated by the this kind of matrix entry of the form Aij. Okay, so here I and j are just indices between 1 and n. Okay, so these are the matrix labels, and the A is just an element in your algebra. Then you have the same notation for the BKL, right? And so what we are saying is just that we can define a unique invariant antisymmetric biderivation, which is completely determined on generators of this coordinate ring by the following fact. You require equation 1, which tells you that to compute this bracket, you compute first the double bracket of A and B. Okay, so this is according to this definition above. Let's say that we have a double bracket, we can compute this thing. Okay, then so we use some Swidler's notation here to say that we just write this double bracket as being something a prime tensor, something second. Okay, so here let's be careful that there can be several terms, and we can have linear combinations appearing here. So it's just a very strong notation. Okay, but we will do everything up to linear terms, so everything will be working very well, as you will see. Yeah. And then the rule is the following. Once you've computed this double bracket, what you do is that you look at the indices that you had in the first place. Okay, so the indices that we had were I, J, K, L. Okay, and then what you do is you take the third index, the K, you put it in here as the first index of the first tensor factor of the double bracket that you've computed. And then as the second index here, you take the J, okay, so the second index of the Aij, right? And then you do something similar on the right. You take the IL entry of the second tensor factor that was appearing in your double bracket. Okay. And at the moment, it may look mysterious, but the point is that if you do that, you have a well-defined operation, which, as I was saying, is an antisymmetric biderivation because of the rules 1, 2, 3 of a double bracket that are written above. Okay. So this is something very nice, and in fact, what Vandenberg proved is not this simple theorem alone, but really what he said is also, okay, as we will see, there is a notion of a double Jacobi identity for a double bracket, and if the double bracket satisfies it, then this antisymmetric biderivation on representation spaces is in fact a Poisson bracket. So you get more from this story. Right, so this was just a very quick idea of what a double bracket is, but before going a bit deeper into the theory, what I just wanted to tell you is why you should really care about those things. And what I've been in some way emphasizing so far is that there is in some way, this is a starting point for non-commutative Poisson geometry. Okay, so from this idea that you can induce usual Poisson structure on a representation spaces, so there is it's interesting to just look at these double Poisson brackets on their own. Okay, but what I will also want to emphasize is that there is some relation to other important algebraic structure. Okay, so you will see that some Leibniz brackets will just pop up along the way very quickly in connection to these double Poisson brackets. Okay, so you can find very nice examples from double Poisson brackets, and also the notion of H0 Poisson structure. And something that I just want to write on is because I came from the field of integrable system, and it's really by studying these integrable system that I was attracted to the double Poisson brackets, and I thought that this was a very powerful theory to develop. All right, so let me know if there is any question about the motivations, but if not, we can go a bit deeper into the theory of double brackets and how they relate to other algebraic structures that are very well known. Seems good. Great. Right, so let's see again this definition of a double Poisson bracket that was there 2 slides ago. So just remember, a double bracket, the important thing is that this is something that takes 2 elements in an algebra and pops you something in a tensor A. Okay, so this is the main difference with anything else you may have seen. It's the fact that it's valued in a tensor A. And then, as I was saying, there are some rules, a rule of antisymmetry and some rules of derivations. So to go from a double bracket to a double Poisson bracket, we need an analog of the Jacobi identity. Okay, and so following van den Bergh, what you can do is define here this double Jacobiator in some sense. So, I mean, this operation looks a bit silly, or maybe looking a bit, I don't know, a bit either impressive or not, I don't know, on the first time you look at it. But if you look at the usual Jacobiator, really the way you would write it is just you take the sum over permutation of what? Okay, so you will just permute 3 elements in an algebra or vector space that you are considering. And then what you are doing is just, well, you would be applying your Lie bracket to 2 elements, okay? You would be doing nothing to the 3rd element. And then once you've done that with a usual Lie bracket, then, well, with the second guy, you just get an element in your algebra. So you get 2 elements in your algebra here. And then what you can just do is say, okay, well, let's apply now the Lie bracket again. And really, that's it. That's your usual Jacobi identity that is written. So as you see, the main difference that we have in our story is that because the double bracket is valued in a tensor A, well, the second time you will be applying the double bracket, okay, you have to be careful, okay? So this is why now you have the double bracket appearing in the first place tensor identity, okay? Because after applying here to this first operation, identity tensor double bracket, we still end up with something in a tensor A, tensor A. And then, as you see here, there is a need to resymmetrize thing after all your operation, because again, we end up in a tensor 3. Okay, so things can be messing around. Okay, so this is just to give you a way to see that, I mean, things are kind of let's say a natural generalization of the of a Jacobiator, but you have to be careful because you end up in a tensor 3. Right. But assuming that you're happy with this operation, okay, and well, I mean, if you want, it's explicitly written here below what this operation is doing on 3 elements A, B, C. But assuming that you are happy with this notion, then, I mean, you can just define what is a double bracket, what is a double Poisson bracket. And a double Poisson bracket will just be a double bracket such that this double Jacobiator is 0. Okay, so what we will say that the double Jacobi identity holds. Right. So as you will see, there will be some nice consequences of this fact. But okay, well, before seeing consequences, let's see examples. Okay, because now you may be thinking that sorry, you may be thinking that I'm saying a lot, but you may be missing examples. So the first thing to do is just, let's go here to this, well, let's just look at the first sign in both examples that are written. Okay, so an example of a double Poisson bracket here on the free algebra in one generator. Okay, so just polynomial algebra in one generator will be given by this double bracket, where you take the generator, well, you take the double bracket of the generator with itself, and you say that it's the generator tensor 1 minus 1 tensor the generator. So here is something very nice appearing already with a double bracket, is that the double bracket of an element with itself is not necessarily 0. It can be very well, okay, it can be complicated. Okay? It doesn't need to be very simple. And then below you have another example that is a bit maybe nicer. Okay, so you have a free algebra on two generators, X and Y. And then you just say in some way that the double bracket of these two generators, X and Y, is kind of a pairing them canonically. Okay, so it's returning one tensor one on these two. And then it's just 0 on if you take twice X or if you take the Y twice. And in these two examples, just specifying like this, the double bracket on the generator, it's enough to know its value on anything. Okay, because if I go back one side and you look up again at this definition, you have derivation rules. Okay, so you have the rules 2 and 3, which allow you to just iteratively, as usual, just obtain the double bracket on any element from just its value on generators. So that's why I've just written these things. Yeah. So now what I also want to emphasize is with this relation with the proposition that we saw earlier, again, this connection to the Kontsevich-Rosenberg principle, is that earlier I told you that if you have a double bracket, then on representation space, you get an antisymmetric biderivation satisfying this relation here. Okay, so this is equation 1 that appeared earlier. So here the proposition is basically telling you that this double Jacobi identity, it's really what you need in order to get a Poisson bracket on representation spaces. Because if you have a double Poisson algebra, meaning, as I was saying, that the double Jacobi identity is satisfied, then this operation here, this bracket, is in fact a Poisson bracket on the representation spaces. Sorry again. Right. So this is why this this operation is very important. Okay. And so now let me just explain on these two examples how they relate to the proposition. So how you compute this induced Poisson bracket. Okay. So for example, if you look at this first example here, when you want to look at what is the nth representation space of this free algebra in one variable, well, basically to understand what is a point on that representation space, you just need to know how to think of the generator X as an n times n matrix. Okay, so this is just isomorphic to the set of all the n times n matrices, capital X. Okay, and if I use again this this notation for the elements of my coordinate rings, little x ij of a matrix in the representation space is returning me the ij entry of this matrix. Okay, so this is really the notation that I introduced before. Then, in terms of these elementary functions, what's happening is that the proposition is telling you that the Poisson brackets takes this form here. Okay. And if you look at that, well, this is really the Poisson bracket that you obtain dually from the Lie bracket on n times n matrices. Okay, because if now you just think of this X as being if you think of Xij as being the elementary matrix with entry 1 in position ij and 0 everywhere else, then here you just think of the commutator of the matrix Eij, EKL, and you see that you get that. Okay, so this is the usual game. Up to a sign. Okay, so this was an example of application of this formula from equation 1. And then another example, it's here. Okay, so with that one, what's happening is that the Xij, YKL are equal to delta Kj, delta IL. And then the Poisson bracket of the X entries or the Y entries between themselves are just 0. Okay, so what you get in particular in that second case is really, it's just the cotangent space of GLN. Are there any questions, maybe? Okay, so if not, I will continue. Right, so, well, okay, maybe I should go back to these two examples. And if you look at those, then what you will see is that the two algebras that I've picked, there are just basically the free algebra generated by a simple vector space. Okay, so in the first case, just a one-dimensional vector space with generator X. And in the second case, we take the free algebra generated by the two-dimensional vector space with generators X and Y. Well, with basis elements X and Y. Okay, so this point of view is convenient to get first connection with some other structures. Okay, so the thing is that, sorry again for coughing, but I've been a bit sick last week, so hopefully my throat will stay okay until the end of the talk. Right, so what I was saying is that whenever your algebra is like that, is just the free algebra generated by some vector space, okay, then there is in fact a related notion not of a double Poisson algebra, where you have a double bracket on your algebra, but of a double Lie algebra, where this time you take all the same actions, you just forget about the derivation rules, but you take these actions on a vector space. Okay, so this is the notion of a double Lie algebra. Okay, and then what's quite nice is that this notion, even though it appeared quite recently, it's also related to some, in some way, a bit older construction, which are skew-symmetric solution to the associative Young-Baxter equation and skew-symmetric Rota-Baxter operators. Okay. So these are things that were first, okay, so the connection between these double Lie brackets and skew-symmetric solution to the associative Young-Baxter equation, it's really due to Schedler first, but it's also well explained in other ski roots of Sokolov. And then the relation to skew-symmetric Rota-Baxter operator, it was really used by Goncharov and Kolesnikov a few years later on. So these, and in particular, these two works here of the ski groups, so Sokolov and Goncharov-Kolesnikov, they're quite nice because they allow to get some classifications of new double Poisson algebras using these classification from the associative Young-Baxter equation world and the Rota-Baxter operator world. So I will not say too much about that, but this is a very nice connection that exists. Right, so let's now go from double brackets to Leibniz brackets, because I mentioned that earlier. Okay, so the first thing is to remember that whenever I'm giving you a double bracket like this, okay, so such an operation, just remember it's taking two elements in your algebra, and then it's popping you something in a tensor A. Okay, so what you can then do is just apply here the multiplication map. And then you end up with an operation which takes two elements in your algebra, returns something in the algebra itself. Okay, so it looks a bit more classical. And you can ask yourself, what is this thing doing? Okay, so this is this notation square bracket that I will use for this operation of computing the double bracket and then multiplying the two factors. Right. And so what is happening is, first thing, this lemma of van den Bergh. So van den Bergh noticed that here the left-hand side, okay, so the left-hand side, if you know left Leibniz brackets, you will directly recognize it. But this left-hand side, it's basically, in some way, if it was equal to 0, it would tell you that this bracket is a derivation over itself. Okay, so it's acting on itself by derivations. Okay, and the lemma of van den Bergh that I've written here, it's basically telling you that the failure of this bracket to act as a derivation on itself, it's completely determined here by the right-hand side. And the right-hand side, it's something obtained by just computing this double Jacobiator that I mentioned earlier. Okay, and then applying some multiplication map. Right. So the silly thing to say is just, well, okay, when this double Jacobiator is 0, okay, which is the case for a double Poisson bracket by definition, well, the right-hand side is 0, so it means that by the lemma, the left-hand side is 0. So in that case, what you get is that this associated bracket is a left Leibniz bracket. Okay. But what is quite nice is that this is not all. You have other properties. Okay, so the first one is that this associated bracket, which is a Leibniz bracket, becomes a derivation in its second argument. Okay, and this is very easy to see once you remember what is the definition of the right derivation rule. So the right derivation rule, it's basically telling you that you just have to multiply on the left factor here, and on the right factor. Okay, so let me just write this. Okay, so I've written the first part. See, right? So this is what the derivation rule for the double bracket is telling you. And then it's very silly, but once you apply the multiplication map here, you just forget about your tensor factor, okay? And so you just have a usual derivation. And something a bit less trivial to realize, it's the second property that is written here, is that whenever you consider a commutator in the first argument, okay, so whenever you consider something of the form AB minus BA, okay, then this gives you the 0 derivation. Okay, so this vanishes on commutators in the first argument. But you have to be careful. You don't have the opposite, okay? So you are not a derivation when you fix the second argument, and you are not vanishing on commutators in the second argument. Okay, so there is something missing there. But apart from that, it's very nice. Are there any questions? Right. Okay, then let's continue. And let's try to build up on this fact that I've just said, that it's a bit antisymmetric in the first and second argument, this associated bracket. Okay, so things are not behaving in the same way. So to try to counteract this lack of symmetry between the two arguments of the associated bracket, what we will do is go to the zeroth Hochschild homology group of A, okay, which basically just means that we consider the vector space A modulo commutators. Okay, and then what you have on this vector space, okay, is that in fact this associated bracket descends to that vector space. Okay, so meaning that while I was telling you that you can factor through commutators in the first argument, what you can also do is to say that, okay, if there is a commutator appearing in the second argument, then you get something which is itself a commutator. It's not 0, but it's a commutator. So this map is well defined. And really, it's not hard to do this computation. It's very easy to do it from the definition. But what's happening is a bit more, because this map that you obtain on this vector space H0 of A, it's not, sorry again, it's not any kind of map, okay, because the associated bracket was a Leibniz bracket, okay, so the Leibniz, well, okay, the Leibniz identity in this sense, okay, this left-hand side being 0 is still true for the mapper sharp here modulo commutators. Okay, but in fact, you can also show that modulo commutator, this operation is antisymmetric. Again, so it's well known that then what you get is just a Lie bracket, because this previous identity being 0, it's equivalent to Jacobi identity, as many people may know. Right, so here is something else which is very nice, is that from a double Poisson bracket, you can get a Lie bracket free by just in some way quotienting out by all commutators. Right. And then what you have, if you just sum up the different nice properties that you've obtained, is that we've obtained a Lie bracket on this vector space H0 of A, okay, which is such that, well, in fact, it was lifting to some derivations. Okay, so this is a property that we noticed earlier here. So this property here of being a Lie bracket that lifts to derivation, it's a notion of H0 Poisson structure that is due to Crowley-Bouvier. And as you will see, this is a very important structure. All right. So to make you put this notion of H0 Poisson structure in a broader picture, let's just go back to the very first thing that I said. So the very first thing that I said is that by the work of Bergh, whenever you have a double Poisson algebra, okay, you can induce on a representation space a Poisson bracket. And I said, okay, this Poisson bracket, it's not anything. It's in fact also a GLN invariant. Okay, so I forgot to say, but you have a GLN invariance by change of basis, because you consider representation acting on a vector space. So you can change the vector, sorry, the basis of that vector space. This gives you a well-defined action. Okay, the point is then that, well, if you further assume that the field is algebraically closed, you can look at the GID quotient here, where you, well, basically look at its variant function in the coordinate ring of your representation space, okay? And this thing will inherit your Poisson bracket, okay? So the point of this H0 Poisson structure is that they are the non-commutative analog of the operation appearing here on the bottom right, okay? Because as we have just seen, when you have a double Poisson bracket, you can construct a Leibniz bracket by just multiplying the two factors in your double bracket, and then you get your H0 Poisson structure by taking everything modulo commutators. Yeah. And the operation that you get here, it's, I mean, it's not too hard to prove it, but this is really the operation that is inducing the Poisson bracket here on the right. And this is something universal, okay? So there also exists some H0 Poisson structure that do not come from some double Poisson algebra, but are still inducing a Poisson bracket here on the bottom right. Right, so this was for a nice picture. And so the way I will go to the second part of the talk is in some way by asking the question, are there any other ways to get some diagram like that using maybe another notion than a double Poisson bracket? Okay, so can we always, well, are there other structure that gives us a Poisson bracket on the bottom right here on this representation space modulo commutate, on this representation space after taking the GID quotient? Okay, there is a moment map version that I don't have time to explain. So going back to my question, are there other interesting variants? Okay, and so just to give you some idea of the theories that exist at the moment, there is a notion of double quasi-Poisson bracket. Okay, so if you know quasi-Poisson geometry, this is the non-commutative version of that. Okay, if you don't know it, the only idea that you should have in mind is that it's quasi-Poisson geometry. it's a setup where the Jacobi identity is not satisfied, but there is some defect controlled by a Lie group. And so when you look at invariant function under your Lie group action, this defect disappears and you have a genuine Poisson bracket. And so in some way, the thing is that Bergh was able to understand that on associative algebras, which is very nice. But I will not have time to talk about that today. Something else that I will not have time to mention anymore is that there is a notion of a modified double Poisson bracket. So this is an idea of Artamanov. Okay, and so what it did is to, in some way, was to say, okay, there is this notion of cyclic antisymmetry, these derivation rules, and that double Jacobi identity that are the three important things for the double Poisson bracket. And in some way, he said, okay, let's keep the derivation rules because they are very important. But let's say that the skew symmetry and the Jacobi identity are only satisfied up to commutators. Okay, because he noticed that when you go to representation spaces, you may just need these things to hold up to commutators when you go to this when you go to the GIT quotient here, rep n a mod GLN. Okay, so this is what he noticed. And the only thing that I want to say on that line is that his theory is really nice, but there were very few examples because his theory is not really symmetric because it's only skew symmetric up to commutators. So there were few examples, some conjectures. And very recently, there was a paper of Goncharov and Gubarev who introduced something related to lambda skew symmetric Rota-Baxter operators of some weight lambda, something that, I mean, you have to look at their paper to understand. But the point is that their theory induces many examples of modified double Poisson brackets. So this is something very nice to say. But so the thing is that so far, nobody has tried to modify the derivation rules of a double Poisson bracket. And so the thing that I will do for the next 15 minutes is just tell you, well, what are the kind of properties that can arise when you try to modify that, and also what can go wrong. But before I move on to that other topic, are there any questions? If not, okay, let's continue and go to this idea of changing the derivation rules. Okay, so in order to understand the change of derivation rules, we have to write down again the same definition of a double bracket, but we need to understand it. Okay. And so what I will do now is just rewrite the outer derivations, the outer derivation and inner derivations in terms of some bimodular structures. Okay, so the outer bimodular structure on A tensor A will just basically be multiplying on the left factor, the left factor on the left, the right factor on the right as before. But okay, as you see, you are multiplying on the outside. And then you have your inner bimodular structure, which multiply on the left the second factor and on the right the first factor. So it's going to multiply from the inside. Okay, so this is where the name obviously comes from. And here is the point. So now in terms of this outer bimodular structure, then when we are considering the derivation rule in the second argument of a double bracket, what we are really using is the outer bimodular structure. And when we are using when we are writing the derivation rule with respect to the first argument of this double bracket, we are looking at the inner bimodular structure. Okay. So why am I doing that? Because now I want to understand what's the relation between these two bimodular structures that allows the theory to work. Okay. And the whole theory is working for two reasons. Okay, so the first reason is that when you have rules 1 and 2, you can always deduce rule number 3. Okay, so my way of saying that is just that the inner bimodular structure, it's a corollary of the outer bimodular structure and the swap map, the tau 1, 2 that we had earlier. Okay, so this is what's written here. If I want to multiply with the inner bimodular structure something, this d prime tensor d second. Then what I just need to do is just swap the two arguments in d prime tensor d second. So I'm applying this swap map to 1 to 1s. Then I'm multiplying, okay, so this is your first step. You just apply the swap map once. Then second step, you multiply with the outer bimodular structure. Okay, so you multiply with the first one, not the inner one that you want. But to recover the inner bimodular structure, you need to reswap again. Okay. So this is what I mean by the fact that the inner bimodular structure is the swap of the outer one, is that you can always get it back from the outer bimodular structure by swapping in some way twice your two factors in the tensor product. I mean, this is a very basic observation, but that's how you get new examples, by understanding that. Okay, and then the second thing that I want to observe is that the fact that the two derivation rules 2 and 3 are well defined. Okay, so the fact that they are compatible is just because, well, the outer and inner bimodular structure commutes between themselves. Okay, so this is a nice thing. And if now I'm using this jargon that I want to use, if I'm saying that the inner bimodular structure is the swap of the outer bimodular structure, the fact that the inner and the outer bimodular structure commute, I rephrase that by saying that the outer bimodular structure is swap commuting. Okay, so it's commuting with the bimodule that you get after applying this swap from observation 1. Okay, so this is something that seems a bit long to do, and it looks like I'm not adding anything to the theory, but now we can really try to get new examples. Okay, and so you can say, well, if you take an arbitrary bimodule structure on A tensor A, okay, so this dot, okay, then you can define as before the swap, which we denote by star, okay, star being the swap of the dot bimodular structure, by just doing that. Okay, so if you want to define it, you first do tau 1, 2 of your two factor, then you apply this bimodular structure that you have fixed in the first place, and then you reswap again everything. And then the second part of the definition, as I was saying, is just that it's swap commuting if these two operations, the fixed one, the dot, and the star that we've defined there, they just commute as usual. Okay. And so here are some examples if you want. So the outer and inner bimodular structure, we've seen them before. So these two are swap commuting. And in fact, we've seen that they are the swap of each other. Okay, so these two are, you can just get one and applying the swap to the other and vice versa. And in the same way, you can do that for what I call the left and right bimodular structures. Okay, so as their name says, the left bimodular structure will just be multiplying the left factor. It's not touching the right factor at all. And the right bimodule is doing the opposite. It's just touching the right factor and is doing nothing with the left one. Right. So these are the kind of things that you can do. But now we can go towards some new notion. Okay. Okay, and there are also twists, but I don't have time to talk about that. Okay, so we can now go towards a generalization of these double brackets. And this is following some joint work with Colin McCulloch. Okay, so here is the definition. So we fix a swap commuting A bimodular structure dot, okay? And as in the previous slide, we denote its swap by star, okay? So again, if you don't really have something in mind, just fix the dot as being the outer bimodular structure, and then the star, you fix it to be the inner bimodular structure, and we will be back in the definition of van den Bergh. Okay, and then we say that the double bracket is associated with this dot bimodular structure. Okay, so the fact that it's associated with this dot will just be saying that we use this bimodular structure to define the right derivation rules. Okay, so the derivation rule in the right argument. But as you see, I'm keeping the cyclic antisymmetry rule of van den Bergh. Okay, so that one doesn't change. The only thing that are changing are the rules 2 and 3. Okay. And so, yes, as I was saying, if you take the author bimodular structure as your choice for the dot, this is just whatever I was speaking about in the first part of this presentation. Right. So here is a nice and in some way simple remark. It's a nice exercise that if you, instead of looking at a double bracket, okay, so according to this generalized definition here, okay, and you say, okay, what's happening if I just swap the two factor and just try to see what's the theory giving me? And this just amounts to replacing the dot bimodular structure by swap the star. Okay, so it means that really you can get some related theories when you are studying double brackets associated with a bimodular structure or its swap. Okay, and so a quick examples about that would be the inner case. Okay, so meaning that we take a double bracket associated with the inner bimodular structure. Okay, so in that case, for some reason that doesn't happen all the time, but it still makes sense to talk about double Poisson bracket where the double Jacobiator is 0. Okay, so there we can do that, and then you have the following analog of what was happening in the case of van den Bergh. Okay, so if you take such a double bracket associated with the inner bimodular structure. So again, be careful, we are no longer in the case of van den Bergh. We are doing an analog, but with another derivation rule for the inner bimodular structure. Then what's happening is that the operation that you get here after multiplying, okay, so the operation here, obtained by multiplying the two tensor factor, becomes this time not a left Leibniz bracket, but a right Leibniz bracket. Okay, and I mean, this is very fun because many people know that if you, sorry again, if you start with, for example, a left Leibniz bracket, you swap the two arguments, then you get a right Leibniz bracket. In some way, this first part of the proposition says that this is kind of a lift to double brackets. That if you take the outer bimodular structure and go to the inner bimodular structure, you will, after multiplication, go from a left Leibniz bracket to a right Leibniz bracket. So this is something very nice. And then this thing enjoys the same properties as before. So you have an analogous notion of a H0 Poisson structure. And then again, you can induce an operation on representation spaces. Okay, and here is the thing that I want to emphasize a lot, okay? So if you remember what I told you earlier is that in the case of van den Bergh's theory, okay, so in the case associated with the outer bimodular structure, then when you want to compute the Poisson bracket on a representation spaces, you had to take the indices after computing the double bracket, you had to take the indices kj, il. Here, as you say, it's the opposite, okay? So we take il, kj. Okay, so in some way, as you see here, the bimodular structure tells you that if it's changing, you are changing the indices on representation spaces. And obviously, the two theories are, as I was saying earlier, that are kind of equivalent, but still, you have to be careful about. And then this thing descends to a Poisson bracket on the GIT quotient, which is also very nice. Right. So this was for the inner case, the basic easy one. And now what I just want to say, and hopefully I will be able to do everything in 5 minutes. I want to say what would be happening for the right case. But the problem is that things will not go well with the double Jacobi identity. Okay, because so the fact that the double Jacobi identity is meaningful in the previous cases, okay, so if associated with van den Bergh theory and the outer bimodular structure or the inner bimodular structure, everything is working because knowing that the double Jacobiator is 0 can it suffices for you to check it on generators. Okay, but this is not always a fact for any bimodular structure. Okay, so if you consider a double bracket associated with the right bimodular structure, okay, so let me maybe just write down what it means so that you see really the difference with the previous axiom. So it means that whenever I'm taking this double bracket of A with the product BC, then what you will write is that you get AB prime tensor AB second C. Okay, so that term is as before, but then the second terms, it's a bit different. It will be AB prime, AC prime tensor B. Okay, so the B is now appearing on the left of the second factor. Okay, and because of this change, okay, you can check that the operation that I'm giving you here on the free algebra on 2 generators as a double Jacobiator, which is 0 on generators, but it's non-zero identically. Okay, so this is something that in some way seems to suggest that the theory is very ill-defined in general. Okay, so so the way to go against that, and I'm sorry, I will have to go quickly over this, even though it's a bit technical, but at least you will have the idea of what's going on. The way to be able to salvage something here is to say that, well, instead of just considering that the Jacobiator should be 0, maybe we need to take the Jacobiator minus something, and the something will be the double Jacobiator itself, but it will be pre and post composed with some permutations. Okay, so this is, I mean, something that needs to be done. And then if we take the permutations and we call them sigma and sigma prime, then we call this the sigma sigma prime weak double Jacobiator. Okay. And so then you can define as before that you have a double sigma sigma prime weak Poisson bracket if this sigma sigma prime weak double Jacobiator is 0. Okay, so this is the natural thing to do. And something, yes, that I will not say is that you can check that basically there are just 3 cases of such a different double sigma sigma prime weak Poisson brackets. Okay, so why am I saying that? Well, just in 2 seconds, because in the right case, you need to consider a double weak Jacobiator. Okay, so the fact is that the double Jacobiator, as we saw, is behaving badly. Okay, so the real reason is that it's no longer a derivation in all of its argument. Okay, but what's happening is that the 1-2 weak double Jacobiators, so when you take sigma equals sigma prime is equal to 1-2, this operation is a derivation in all of its argument. Okay, so it's meaningful to say that we can consider double 1-2 weak Poisson bracket when we consider the double bracket associated with the right bimodular structure. Okay. And then if you do that, well, you can study this notion. Okay, and so I will skip these 2 cases because I may not have much time. I just want to explain what's happening on representation spaces. Okay, so if you consider now a double bracket associated with this right bimodular structure, and you assume furthermore that it's a double 1-2 weak Poisson bracket in the sense of the previous slide, okay, then what's happening is that on a representation spaces, okay, you get a Poisson bracket again in the same way as you got it before. But now look, again, the indices have been changed. It's no longer KJIL or ILKJ, it's IJKL. Okay, and here, in some way, it's KL because you only multiply on the right factor. So it's normal that the KL is staying on the right. So this is the very nice thing that I wanted to say there. And this operation also descends to the GIT quotient. But I'm lacking time, so I will finish. Okay, so the left case is basically obtained from the right case from a similar idea, but I will finish now. Thank you very much for your attention.
Thank you for your interesting talk. Other questions?
Yes, I have a question.
Yeah. Yeah, you can speak.
In the right case, do you also have a Leibniz bracket? In this last 1-2 week Jacobi
yes.
right case.
Thank you for asking the question. So in some way, here the proposition is something different, okay? And the main problem is that in the right case, if you multiply the two arguments, you no longer have derivation rules in any of the two arguments, because I mean you've concatenated the two. So in some way, this operation is no longer in some way interesting at all. No, it's not. That is the puzzling thing. You don't get a Leibniz bracket at all. Okay. It's just not working.
Okay, and I have a comment to make. Maybe you know work from Joan Leray.
Yes.
Okay.
Yeah.
Okay. Just wanted to bring it to your attention. He worked about double Poisson properade and showed that it is co-sul in some way. So.
Yes. Well, thank you for bringing that up. Yes, I've never met Joan Leray, but he's done some very interesting thing, and also in connection to these pre-Calabi-Yau algebras that I've not had time to explain because I'm more only in. Well, I don't really know that. So thank you.
Exactly.
Yeah.
Thank you. We also have a question in the chat.
Oh, okay. Let me open it. So is the double bracket theory related to some kind of deformation theory? That's a good question. And I mean, in some way, if you go on Mass Overflow, there is an old question of Damien Calac from 10 years ago, or even more, asking if there is some kind of deformation quantization based on double Poisson brackets. And I've been discussing that with him a lot. And while we don't have examples yet, it seems that the idea would be that maybe there is a way to deform the Poisson bracket on the representation space using maybe some obstruction theory on the double Poisson bracket. But I mean, this is still just a naive guess, okay? We've not done any serious work in any direction, and nobody else, as far as I know. But that's a very interesting question. Very interesting.
Thank you. Other questions? More questions? Okay, we have no question, and so we resume next week. So see you. Thank you for your talk.
Thank you.